So we'll look at some applications now, including quite important ones. And these are really applications in the very genuine sense that the statement is not about algebraic topology. In fact, it's barely about topology. It's about continuous functions on quite familiar spaces, ones you would study in real life. So first is of a little more technical nature, but it's interesting, and it's what we use for the second one. Okay, so this says there is no retraction. Let me just spell that out. There is no map R from the disk to disk, the usual to disk, to the circle, such that we'll write it as a commutative diagram. So S1 is of course included into the to disk, and there is a retraction R. Maybe I should dash that because this does not exist. Okay, and here we are, R, such that this thing commutes. Okay, that is, now that I have this picture, let me call this inclusion. That is simply that R composed with inclusion is the identity of S1. Okay, and the proof is a classic application of a functor. Okay, but first we can get a free upgrade, because you see, if such an R exists, proof, if R exists, okay, we get, so S11, so R has to be, a retraction is something which on the subspace is the identity, so 1 has to go to 1. So S11 is mapped by inclusion I to D2 1, and this is mapped to S11. So fortunately for us, it's automatic that you have a map of based spaces. So this is going to be R, and this is the identity of the pair S11, and hence by functoriality of pi1, that is formally by applying phi f star, we get pi1 of S11, which is mapped by I star to pi1 of D2 and 1. This is mapped by the identity. That's crucial. We know that it's the identity. Identity star, okay, to pi1 of S11. Okay, again, a property of identity that I did not state explicitly is this identity is the identity on what? Well, this group is Z. We saw that. This group is Z. So this is identity on the group of integers, additive group of integers. But this group is 0. And so Z will have to be, so this map will have to be 0. And this map, which is R star, is also going to be 0. 0 composed with 0 is certainly not the identity. Okay, so this is impossible. So this is a classic application of the functor with a little bit of a twist, where namely the twist was just that we noticed that we could look at this as a map of based spaces, not just as spaces, because we have functoriality only at the base spaces. Okay, and now from this we get one of the most famous results, which is an application of topology, the so-called Brouwer fixed point theorem. And what this Brouwer fixed point theorem says, that any map, which recall is continuous function, f from D2 to D2 has a fixed point. And fixed point, recall, is that is there exists x in D2 such that its image is itself f of x equals x. Okay, and the proof is by contradiction. Okay, so suppose f, and suppose we had some map f from D2 to D2 has no fixed points. Then we'll construct a retraction. Okay, we construct a retraction, and I'll draw a picture of that with retraction R from D2 to S1. Okay, so let's draw a picture. Here is the disk. That's a pretty terrible circle. Let's try a little better. just slightly better. That's pretty bad too, but it'll have to do. So namely what we do is we take the point x and let's look at f of x. And let's look at the line that starts at f of x and goes towards x. Okay. And let's make it actually a straight line. It starts at f of x, goes towards x, and we keep continuing this till it hits the circle. And the point at which it hits the circle is going to be r of x. So this point here, this is going to be r of x. Okay, so let's put some formulas for this. I'm going to leave it as an exercise that this is continuous. It takes a little bit of work to show that this is continuous. Okay, you could even write an explicit formula and use that to work it out. But first let's see how do we draw this line. So this line is given by well, it's really a ray, so let me call it rho x from 0 infinity to the plane be rho x of t. You simply use the formula for convex linear combinations. 1 minus t times f of x plus t times x. So note at t is 0 you're at f of x, t is 1 you're at x, but it continues where t is greater than or equal to 0. Now it could happen that f of x itself was on the boundary, then you don't want to take it as f of x. Otherwise it would be discontinuous. Okay, and so let tx be the infimum, the smallest. There are a few different equivalent ways of writing it, of t greater than or equal to 1, such that rho x of t is outside the circle. So norm rho x of t is greater than or equal to 1. Okay, a special case here is quite important. Suppose I had x was actually on the boundary of this circle and f of x was somewhere. It could be in the interior or it could be in the boundary. We'll do the interior case in a moment. Then what we do is we draw this line. Oh, it's not a line here. So we draw this line, and the first time that it hits the boundary is actually t equals 1. So in that case capital T of x is actually 1. We'll remark on that. By the way, it could be that you started off on the boundary and then ended up here. Okay, so in that case, so that would be a case where it's not this point but this point that is f of x. In that case you don't want t to be 0, which is on the boundary, otherwise you get discontinuity. Nearby x will typically have, so if I took a nearby x prime, f of x prime could be slightly in the interior, and you get a discontinuity because these two are very close to each other, but t is here, 0 here, and t is 1 here. But I haven't told you what r is in terms of t. Okay, so let r of x is going to be the value of rho x of tx. Namely, I look at the first time that you exit the circle after having reached x and see where you exit the circle at that point. So now here I can say it clearly. What happens is that if f of x prime is slightly inside, it was here, then the first time you exit the circle will be x prime. But if it actually was at the boundary, if you allowed 0, you would have a problem. Okay, so what we do is we go from f of x to x and then continue till we hit the circle. So in particular, okay, so observe first of all that if x is in S1, if x has the boundary, then tx of x, tx, is it called just tx, is actually equal to 1. The time when you hit the boundary is 1, and r of x, which is going to be rho x of tx, is just x itself. So we do have a retraction, and also that r is continuous. Okay, this takes a little bit of work. It takes a little bit of work because, well, there are a couple of ways of doing it. One is you could just work out a formula, do a little bit of geometry and work out a formula. But the other way is that we have x and f of x, and if I have a nearby point x prime and I have a nearby time, then f of x prime will be somewhere near this. and I want to know what happens to the nearby line. I want to claim that it hits the circle. Let's make it a line again. So let's claim that it hits the circle somewhere nearby. Okay, so this time this in this light shade of blue is not a line. This guy is R of x prime. How do I know they're close? Well, you do it in 2 steps. R is continuous. Okay, so show if x prime is close to x, then you show that tx prime is close to tx, and then R of x prime is close to Rx. Okay, you have to quantify this a little bit carefully, because how close depends on the distance between x and f of x. So if x and f of x are very close together, then you really have to take a very small neighborhood of x. Okay, you also have to use continuity of f and ensure that you first take maybe a small neighborhood of f of x, you take a small neighborhood of x, look at the inverse image by continuity, and so you have a small set, so the image is also contained in this neighborhood. Okay, there's a little bit of geometry here, and when the image is contained in this neighborhood, it means the starting point and the time one of these 2 line segments are very close to each other. And now you claim that if t of x is 1 at some point, so tx at tx, sorry, the rho x of t has norm 1, then a little later it's strictly positive, and since this line segment is close to that is also strictly positive, so we have taken the infimum. So that will tell you that your new tx prime is less than tx plus epsilon. Reverse the 2 and claim these 2 are equal. Okay, so it's a relatively easy exercise, but it's nice. You have to work out a little bit. Okay, that said, let's appreciate this result. So what we did is the following. We claimed that a function from d2 to d2, from a ball to a ball, has a fixed point. Now this is true in Dn as well, and it has very important applications like the Perron-Frobenius theorem in linear algebra, and even the Nash embedding theorem. So these are because of the concrete nature of the spaces, and we are dealing with continuous functions. This is not even really a topological statement, and it certainly has no algebraic topology in the statement. It's quite an important result in mathematics, and there's a whole bunch of fixed point theorems that you see in algebraic topology. This is the first of them. Its proof again is that you prove it by contradiction by noting that there is a retraction from this nice picture. Okay, so with that we have our first applications.